Hello, the topic for this lesson is quadratic forms. So let's begin with a brief overview of the lesson. So let's say you have this expression over here, q, which is given in terms of two variables x and y. Then you'll notice that each term over here has total degree 2 in x and y. So the first term is x square, that's degree 2. Next one is x raised to 1 and y raised to 1. And then you got y square. So this is an example of a quadratic form in two variables. Now, if you set q to be equal to different values, then what you'd get is a family of ellipses as seen in this contour plot. So you see over here that you have these ellipses over here, and what we want to do in this lesson is to talk about these quadratic forms using symmetric matrices. So that's a very nice application of symmetric matrices. Okay, so let's begin with a formal definition. So let's say you have capital A, which is an n by n symmetric matrix, and your vector x in Rn, then if you form this expression over here, what you get is a quadratic form defined by A. And of course, the matrix A is then called the matrix of the quadratic form. So every time you have a symmetric matrix, you can build the corresponding quadratic form. So as an example, here is a matrix A. It's a very simple diagonal matrix. Let's try and find the quadratic form corresponding to it. And you see over here that you get back a very simple quadratic form. And if you take a slightly more complicated matrix, B, again it's symmetric, then you can again form the quadratic form, but this time it's a bit more complicated. It's got a cross term in it. And notice that this 14 over here is 7 plus 7. Okay, so how about the other way around? So let's say you have a quadratic form like this one over here in variables x1, x2, and x3. Then how do you go from there to the matrix? Well, the coefficients of the square terms will give you the diagonal entries of A. And you want to make A symmetric, so you need to kind of divide the other coefficient into 2's. So here you are. This is the matrix for the quadratic form. So 4, 3, and 1 over here are just the diagonal terms, and they are the square terms over here. And then you have -4, giving you -8, etc. So let's check that the answer is correct by doing the reverse procedure, and you do get back to the same quadratic form, but in perhaps a slightly different order. Okay, so now what happens if you change variables in a quadratic form? So let's say you have a quadratic form Q, and then you have a symmetric matrix A underlying it. And you make a change of variables. X equal to P times Y is a change of variables from X to Y. Then what happens over here is you get a new quadratic form, and the old one, new one are related by this very nice, simple relationship, namely the X transpose the X is Y transpose times that product over here times Y. So that's a very simple transformation for the quadratic form. Okay, so an example here is matrix A, a very simple diagonal matrix. Here's the quadratic form. We choose a matrix P, and we get the kind of transformed quadratic form. But notice that this over here is much more complicated than what you had over there. So you actually get back a more complicated quadratic form. And of course, the interest in going in the reverse direction. You want to start with something like this and go back to something fairly simple as that. Okay, so that's what is called the principal axes theorem. So it says that if you have a quadratic form Q that's defined by a symmetric matrix A, then because A is symmetric, you can compute an orthogonal diagonalization for it. So A is P into D into P transpose, where P is an orthogonal matrix and D is a diagonal matrix. Then if you make the change of variables given by P, then you get back a very nice, simple quadratic form, which has got no cross product terms in it. And these columns over here of P are called the principal axes of the quadratic form. And now this whole procedure itself is called diagonalization of the quadratic form. So an example of that here is a quadratic form Q. It's got a diagonal term over here. Write out the matrix corresponding to it. You see the 4 and 4 here come from the 8 over there. work out the eigenvectors of A, form the matrix P. Here are the new variables, work out the new quadratic form, and you see it's 11y1 square plus y2 square, which is really nice and simple. And of course, the eigenvalues over here are 11 and 1, which are just the terms over there. Okay, so finally, we want to talk about how do you classify quadratic forms. So let's say you have a quadratic form Q corresponding to matrix A. Then this quadratic form actually defines a function from Rn to R. So what you get back every time is a real number, an element of R. Now this quadratic form is said to be positive definite if the value Q of x is positive for all x. It is negative definite if the value of Q of x is negative for all x. And it is indefinite if Q assumes both positive and negative values. So three possibilities: either all the values are positive, or they're all negative, or they might some be positive and some be negative. So here's a nice picture for that. So that's the positive definite case. All the values lie above the xy plane. Negative definite, they all lie below, and indefinite mean that they lie above and below both, like a saddle shape. And the question is, how do you decide which kind of quadratic form you have? So let's say you have an invertible matrix A, invertible symmetric matrix A. You find the corresponding quadratic form. Then this quadratic form is positive definite if and only if all the eigenvalues of A are positive. That's a very nice, simple criterion. So positive definite corresponds to positive eigenvalues. Negative definite corresponds to negative eigenvalues. And indefinite, the middle case, corresponds to the case where the eigenvalues are both positive and negative. And luckily, we have nice functions, positive definite matrix Q and indefinite matrix Q, which can be used to do that for you. So as an example, here is a quadratic form. I'm just going to clear some variables. Here's a quadratic form Q. Here is a contour plot. Now, it's a 3D contour plot over here. And if you look at it, it looks like the quadratic form is going to be kind of indefinite. Let's check that now. So here's the corresponding matrix A. Work out the eigenvalues. You see there are some positive, some negative, and hence is an indefinite quadratic form. Let's check that indefinite matrix Q, and you see that it in fact is indefinite. So that's a very nice, simple way of checking what kind of quadratic form you have. Okay, so it's time for me to summarize the lesson, and the point is that quadratic forms can be represented by a symmetric matrix A. And the eigenvectors of A can be used to diagonalize it to make it simpler, and the eigenvalues of A determine what kind of form it is, whether it's positive definite, negative definite, or indefinite. That's a very nice, simple result. And the next time we'll talk about the singular value decomposition, but I'll stop here for now. Thank you very much.